Good morning, good afternoon, good evening. And today is our great honor to invite Professor Ekram Hossain from University of Manitoba to give us a talk on machine learning-based channel estimation in RIS-Aided wireless system. So before the talk, I would like to introduce Professor Ekram Hossain to you. I believe that many of you already know him pretty well. But as a routine, I will introduce him first. Professor Ekram Hossain is a professor and associate head in the Department of Electrical and Computer Engineering at University of Manitoba, Canada. And he's a member of the College of Lawyers Society of Canada, and he's a fellow of Canadian Academy of Engineering and a fellow of the Engineering Institute of Canada. Dr. Hossain current research interests include design analysis and the optimization beyond 5G cellular wireless network. He was elevated to IEEE fellow for contributions to spectrum management and resource allocation in cognitive and cellular radio networks. He received the 2017 IEEE Consult TCGCC Distinguished Technique Achievement Recognition Award for outstanding technique leadership and achievement in green wireless communications and networking. Dr. Hossain has won many research awards, including the 2017 Communication Society Best Survey Paper Award and the 2011 IEEE Communication Society Fred Elastic Prize Paper Award. And he is listed as a highly cited researcher from 2017 2022. So currently he served as an editor for IEEE Communication on Mobile Computing. Also previously, he served as editor-in-chief of IEEE Press and editor-in-chief of IEEE Communication Surveys and the Tutorial. And also he was a distinguished lecturer for IEEE Communication Society and the IEEE Vehicular Technology Society. So during the talk, please write down your questions and any question you want in the Q&A box or chat box. So we will back to your questions after the talk. So without delay, I will give the floor to Professor Ekram Hossain. Thank you.
Thank you very much, Jigon, for your kind introduction. First of all, thank you for inviting me to give this seminar. So good day, everyone. So the talk is going to be on machine learning-based channel estimation in RIS-based wireless systems. And here is the, I cannot advance it now. Jigon, I think.
Yeah, I can see your slides.
Okay, great. Yeah. Okay, you can see it. Okay. So here is the outline of the talk. I'm going to first talk a little bit about the basics of RIS. I assume that many of you are already familiar with this RIS technology, which is emerging as a potential enabler for future high-speed wireless systems. And I will also talk a little bit about the channel estimation problem. It's kind of a tutorial on this problem, which is a fundamental problem for any wireless system. And specifically, I will mention about the issues related to estimating channel for an RIS-aided system. There are some specific challenges that are associated with these RIS or RIS-based systems. And then I will move on to this specific proposal that we have basically recently developed for channel estimation in RIS-based systems, which is a machine learning-based solution. And then I will conclude. Okay, so as you may already know, this RIS is basically a software-controlled surface that can be programmed to alter electromagnetic response. So basically, as electromagnetic waves impinge on this surface, you can manipulate the response of the surface, right? So that impinging signal can be manipulated, as you want. Okay, and this surface consists of a large array of scattering elements, and they can be re-engineered without refabrication. So basically, you can make them work as you desire. Okay, so and recently, if you are following the literature from the EM community, you will see there will be a lot of work going on this re-engineering of these surfaces. And as I will show you in the next slide, basically you can generate a whole exotic, types of patterns, from these surfaces. So basically a wide range of functions can be achieved, which include reflection, refraction, beam focusing, splitting, wave shaping, polarizing, etc. So basically what happens when an EM wave impinges on the surface, basically you can engineer the response, right? And you can do a lot of things. Reflection, you can, as you want, like the way you want to reflect the wave, you can do it. You can refract, and you can change the polarization, even you can change the frequency, etc. So this is basically very promising, as you can imagine, in with respect to engineering the propagation environment. So you can basically program the propagation environment. So these surfaces are also called electromagnetic metasurfaces, passive intelligent surfaces or mirrors, smart reflector, etc. So there are all sorts of different names for these surfaces. Okay, now if you think in terms of network, like these surfaces can be considered as some network nodes, which are low cost and have low maintenance kind of nodes. These are low maintenance nodes in the sense that you do not need any active RF kind of chains, etc. in these surfaces when they are fully passive. And of course, they need to be controlled. Now, for controlling these surfaces, you can use either some in-band communication channels or some out-of-band channels. And they are full duplex in the sense that, the rays, the signals, they impinge on the surface and they basically, go back or reflected in the same frequency, right? So they're full duplex. Now, what are the good things? Why they are promising? If you think in terms of densification of the network, they are alternative to small cells for expanding the network coverage, because installing those cells, the base stations, is not a very easy thing, right? So they are involve cost, etc. But these surfaces could be cheaper alternatives for network expansion, like to expand network coverage, and also they can be used for front hauling. Okay, so they are basically, in short, they are cheaper alternatives for network densification. And also, as I just mentioned, they can be used also for other purposes, such as front hauling. Now, I will talk a little bit about some specific properties of this RIS. Now, if you have a large aperture RIS, so basically lots of elements, etc., then, oops. Sorry. I am unable to move, it looks like. Okay, so if you have a large aperture RIS, then the near field, if you are familiar with this Fraunhofer distance, right? This basically proportional to the aperture size of the antenna, your near field increases. Now, that can be exploited for some applications such as sensing, etc. So what I'm trying to say, these RIS can be used for both communication and sensing type of applications. So when they operate in the near field, so basically when you have a kind of a large Fraunhofer distance, so that's also called the non-radiative or reactive mode of operation. So basically the waves, they propagate and some of them come back. It's not purely radiative, so it's also called reactive kind of a mode of propagation. So that can be exploited for applications such as sensing. Now, if you go beyond the near field of the surface, then it's purely in the propagation mode, radiative mode. And again, you can have very highly focused kind of radiation, which can enable interference-free communication. So if you can direct your transmission, in a more focused way, then you, as you can guess, avoid interference, etc. And as I also mentioned, even in this mode, you can use, RIS for localization. And beyond that, you can also use RIS for wireless power transfer. In fact, I know that this has been already demonstrated in several other places. I mean, in Korea, I know one of my former postdocs, he was actually showing me, they have developed a test bed to do simultaneous information and power transfer by using this RIS. So basically, in all these applications, you exploit the high focusing capability of RIS. Okay, so here this slide shows some applications, potential applications of RIS. The first thing, as I was mentioning at the beginning, is the coverage expansion, right? So as you see on the top here, so for cell edge users in particular, you can help them to have high communication quality. Also for localization, for simultaneous information and power transfer. Also, RIS could be a good technology for physical layer security. As I said, due to the high focusing capability, you can direct transmission specifically to your intended user. So basically, the eavesdroppers and other attackers may not be able to take advantage. Okay, and yeah, I mean, there could be other applications in terms of smart transportation, etc. Okay, so now I'll briefly go through the signal and channel models that are generally used when we talk about RIS-aided communication. Now, if you think about a single RIS element, so your impinging signal XN is basically now it's in reflection mode. So for example, then the reflected signal you can represent like this, and beta is the reflection coefficient and theta is the phase shift. Now there could be no reflection at all, in which case beta would be 0. So basically the signal is absorbed. For full reflection, beta is 1. Now a surface has lots of elements, right? So if you've got n elements, so basically the signal that comes out of the RIS can be represented like this. So X is the transmitted signal. So and I should say receive signal, right? So the transmitted signal X is basically attenuated, right? Due to these gains here. Okay, so G is the gain between the transmitter and the RIS, and H is from the RIS to the user, for example, and beta, and as we saw before, say if it's a reflection mode of operation, then it could be 1 for full reflection. Theta is that reflection angle. Now this H and G could be complex, right? Because they are complex gains. So simple, right? So this is the baseband kind of a signal model that we generally use when we talk about RIS-based systems. Now, for any communication system, we need to do channel estimation as the first stage, right? Because after you have some estimates of the channel, the gains, etc., if you know the channel estimates, then you can appropriately design your other transmission parameters, say for beamforming, for pre-coding, right, for power allocation, etc. And generally, estimation is done by using pilot signals. That's the most common approach. So basically, the transmitter, for example, can send some pilots, and the receiver side, after receiving the pilots, can estimate the channel, and that should be fed back to the transmitter, etc. Now, these estimates are valid for certain duration, which is called the channel coherence time, right? Now, as I just mentioned, when the pilots are transmitted at the receiving side, they are received, and then based on the received signal and the known transmitted pilots, you can use either least square or MMSE type of standard methods for estimation. Okay, I will talk a little bit more about this later. Now, as I also mentioned, after you have the channel estimates, then you can do system optimization. For any wireless system, this is how it is done, right? You can choose your modulation coding, like in this case, you will be doing optimization of the phase shifts at the RIS, and also optimize the beamforming at the base station, for example, after you have the estimates. And an accurate estimate is critical for good performance of the system. Okay. Now, CSI is basically a form of channel estimate. If you have the channel gains, etc., then you can estimate your CSI. So there are several metrics that can be obtained based on the channel estimate. So CSI is like one of the metric that is related to the channel estimates. Okay, now let's go a little bit more on this signal and transmission model. Say you have got M transmit antennas, and you have got a RIS with N elements. Now here we will be talking on reflection mode, actually. So these are all reflective RIS. And you have got K-receive antennas. Now, this phi vector is basically a vector that denotes the phase shifts for the RIS elements, right? So you've got n elements, so that's why it's a size n here. Each element has a corresponding phase shift value. So the channels, there are 3 channels involved here. Direct channel from the transmitter to the receiver, because you have got M transmit antennas and K-receive antennas, so you can represent the channel like this. And from transmitter to the RIS channel is G. You have got M transmit antennas and got N elements, RIS. So again, you can represent like this. And from RIS to the receiver channel, you have got N RIS elements and K receive antennas. So this is the receiver channel. Now, if you've got a transmitted signal X from the base station, say from the transmitter, right? Using M transmit antennas, so the received signal would be like this. So this is basically the direct part, like the signal that arrives directly to the receiver. And this is what is received via RIS, and this is like the noise. Okay. Now, this is what is called a cascaded channel, because from the transmitter to the RIS to the receiver. So this part is, this is like a cascaded channel. This is like the direct channel, right? Now, as an example, if you've got a SISO system, right, single transmit antenna and single receive antenna, so the received signal will look like this. Okay. Again, this is like the cascaded channel here. Okay. Okay. So now I show you an example, like why we need this channel estimate. So basically, the problem is to estimate these channels, right? S0, G, and HR. So these are the channel matrices. Well, if you can obtain the matrices, then you get the channel information completely. So we need them, right? We need to estimate these channels to design the system parameters, right? So before communication starts, you got to estimate these channels. Now, I'll show you a specific example, like, why we need these estimates for system optimization. So let us consider a MISO system. So M transmit antennas and N RIS elements, and say just single antenna users. So again, the channels will be denoted like this: the direct channel, the channel between the RIS and the receiver, single antenna receiver, and this is G is the channel between the M antenna transmitter and the N element RIS. Okay, now let's say we want to optimize the beamforming vector at the transmitter side, and W is the transmit beamforming vector, right? So if you've got M antenna transmitter, so this is size M, right? W is an M element vector. So we want to optimize it for what? Say to optimize the received signal power, received SNR, or etc., or there could be some other objectives as well. So now in this setup, the received signal at the single antenna receiver is like this, as we saw right before, similar. So direct channel gain, the cascaded channel gain, and the transmit beamforming vector, the signal, and the noise. So with this signal model, we can have the received signal power given like this, right? So say we want to maximize our transmit beamforming vector. We want to optimize our transmit beamforming vector to maximize the received signal power. So basically, you're going to solve this kind of optimization problem, right? So maximize the received signal power, right, subject to your power constraint of the transmitter, and the reflection angles, of course, they're constant like this. And the optimization variables here are the beamforming vector and the phase shifts at the RIS, right? So as you can see here, these values are given, P given, and so to solve for W and phi, we need H0, HR, and Z, right? Right. So in order to solve this problem, of course, you need to have these channel estimates, right? So anyway, so this is just an example to show that, to optimize system performance, you will require this channel estimate. So this is a prerequisite for system optimization. And this also shows an example how do you optimize this kind of RIS-based systems. Okay, so now the question is how to perform this estimation, this H0, HR, Z, right? These matrices, right? Efficiently. And what it means, like with low overhead, preferably with low complexity, low overhead. Now, as I was mentioning at the beginning, in traditional systems, like, traditional cellular systems, the base stations or the users, they can transmit those pilot signals. Say the users send the pilot signals, the base station receive them, and they can use those least square or MMSE type of methods for estimating the channel, and they can send it back. I mean, if it is a TDD kind of, right, so they can exploit the reciprocity, and the transmitters can use those estimates. But in this case of RIS-aided system, if the RIS is fully passive, right, then these RIS cannot send anything by themselves, right? So basically, those type of methods may not be usable, because unlike user devices, they can transmit signals, right? So how can they estimate channels? Say, for example, from the RIS to the base station or RIS to the user. So because they are passive, they are unable to do, unable to transmit these pilots, etc. So this type of traditional methods will not work. So we get to think about some other methods. And as I also mentioned, we want to avoid large control overhead. So this is a basic problem, right? Like when you talk about MIMO system, basic MIMO systems, right? So estimation of the channel is a primary problem. It's one of the most significant problems. And after we have the estimates, then how do you optimize our system, right? How do we choose the optimal configuration? So these are like the fundamental problems in an RIS-based systems. Okay, so now there are two methods, pilot-based methods and prediction-based methods. So I already mentioned about highly how these pilot-based methods work. Now the prediction-based methods are low overhead methods in the sense that you don't need to estimate the channel every coherence time. So basically, based on some previous estimates, you may try to predict instead of trying to send the pilots again and estimating. So here you may leverage some machine learning type of techniques. So basically, you don't send pilots every coherence interval. So you try to predict gas based on your previous estimates. Now, I have to mention that this, the method that I'm going to discuss is still a direct method. It's still a pilot-based. It's not a prediction-based. Okay, but in the literature, if you see, there have been a lot of work actually using machine learning for prediction-based estimation. Quite a number, of course, I should say. Now, going back to this direct method, how do they work? So basically, the channel coherence time is divided into two periods. One period for transmitting the pilots, and then after you have the estimate, then you use the rest of your time for data transmission. And the two most popular methods of pilot-based estimation is least square method and MMSE method, minimum mean square error method. So basically, if you have the transmitted pilots X and the received pilots Y, so use this kind of formula. So I'm not going to the details, but this is kind of a standard. If you look at the textbooks or the papers, I mean, you will come across this formula. So this is how they actually look like. So you have some computation involved here, some inversion, etc. Now the first one, least square method, is generally very simple, but it is known to have low accuracy. Now this MMSE method is generally better. It's a little bit more computationally involved, but it's more accurate. However, it requires some additional information, such as this covariance matrix R, for the channel, right? So this is not a simple thing. So this is the problem with this MMSE method. So now, when we are talking about these direct methods, how does machine learning come into the picture? Now, machine learning techniques can be used to have better computation, in the sense that if you get, say, for example, use a neural network, maybe you just give the pilot outputs Y, and the neural network will give you the channel estimates. So basically, you don't go through these computations, direct computations, right? And also for MMSE, as I said, you need to have this covariance matrix, which may not be easy to obtain, right? So the advantage could be easy computation. If you just feed into the neural network and it gives you the output, and the accuracy could be high. Okay, so yeah, so that's what is written in the last bullet here. When we talk about machine learning based direct channel estimation, we are aiming for a good accuracy with better runtime efficiency. So it's like avoid lots of these computations involving matrix inversion, etc. Okay. Okay, so again, our intention is to estimate these channels direct channel, the channel between the transmitter and the RIS, and the RIS and the receiver. Now, the direct channel estimation would be easy because this is like the conventional system, right? Between the transmitter and the receiver. That channel can be estimated using conventional methods. Now, also two comments on these channels from the base station to the RIS channel. This channel would be rather static because, you know, if you put the RIS in a static location, right? And of course, the base station is fixed. In that kind of scenario, I mean, the channel may be quasi-static, may not change very rapidly. So what it basically implies, estimation of the channel can be done off and on maybe, right? You may not need to do it every now and then. But the RIS and user channel will be more dynamic, right? Because that will vary depending on the user location, etc. So that will need to be, you know, may need to be estimated quite often. Now, as I mentioned, with the fully passive RIS, it's difficult because they cannot send pilot signals, etc. And also, if you think of a large number of elements in the RIS, as well as large number of transmit antennas at the base station, and say also at the receiver side, you have got a lot of antennas. So the matrices, they grow, right? As you can guess, the size of this channel matrix will be very big with large number of antennas, large number of elements, etc. So that makes the estimation also difficult. As you can imagine, I mean, from computation point of view, you will have large matrices, etc. Right? So if you use the traditional methods, of course, they'll be more intensive in computation, right? So that kind of motivates the use of machine learning to use better runtime efficiency. If you've got a very large system, lots of antennas, lots of elements, right? So that might be, you know, computationally more efficient, more, you know, runtime would be better. Okay, so now what we have discussed so far, estimating the channels separately, like from the transmitter to the RIS to the user separately may be difficult because the RIS have only passive elements, right? So as you can see, imagine. So separate channel estimation will be difficult. Now, what you can do, you can estimate the cascaded channel. We know what the cascaded channel is, right? So basically, okay, so if you go back, so H0 is the direct channel and this is the cascaded channel. So if you want to estimate the cascaded channel, it might be all right because the base station, say, for example, transmit the pilot, so the user send pilot and the base station receives, and then you do the estimation, right? Now, you may use this estimate for your system optimization. And for some applications, that might be okay. You don't need to estimate the separate channels. Just the cascaded channel is good, right? Now, if you are interested to estimate the channels separately, that's difficult. Now, mathematically, if you see here, the composite channel, right? The direct channel plus this cascaded channel. Now, you can represent this composite channel like this. And for any diagonal matrix D, right? If you multiply here by D inverse and then also bring D here, it does not change. So what it means, from the composite channel, estimating the separate channels, H, R, and Z separately is difficult due to the ambiguity that is caused by D, right? Because by multiplying by any matrix, any diagonal matrix D, in this way, D inverse here before phi, the phase shift matrix. This is the phase shift matrix. So based on the phase shift vector, you basically build this matrix, phi, and this is this D. So basically, due to the ambiguity caused by D, this is same as this. So estimating H, R, and G is difficult, right? So that's the point. So with completely passive RIS, estimating G and HR separately from the cascaded channel is difficult. So if you are thinking about some factorization, for example, right? Matrix factorization to estimate HR and Z, this is going to be difficult because of this ambiguity, right? Now, as I said, for if you could have this channel separately, it could be advantageous for some applications, right? So our intention is to estimate this channel separately. We want to, we are not happy with only the cascaded channel, but we also want to estimate these channels, separate channels. So that's our objective here. Okay, anyway, so again, just quickly, I would like to go over the approaches that can be used for channel estimation. Now, these are, okay, so the first one is for the case when, okay, your RIS is not fully passive. Say you have a few active elements in the RIS. So those guys can send and receive, etc. right? So these will be called semi-passive RIS. Well, then this is, the problem is kind of similar to the traditional, right? If you have some active elements or sensors in the RIS, you can use the traditional methods for channel estimation, right? Now, if it's fully passive, then as we have already discussed, you cannot estimate the channels separately. You will be estimating the cascaded channels. And majority of the work, if you have followed the work on channel estimation in RIS system, you'll see probably 95% of the work, they basically deal with this cascaded channel, right? So they use either LS or MMSE-based estimation for the cascaded channel, and then they use for optimization. So that's what traditionally people do. Now, for fully passive RIS, due to the difficulty of this estimation of the channels separately, what you can also do, forget about this estimation entirely. Okay, so you say, okay, I'm not going to do explicit channel estimation. I will do optimization on an end-to-end basis, right? So you can think of using some machine learning technique to do, say, beamforming, active beamforming on an end-to-end basis without going to the channel estimation, bypassing the estimation completely, right? So you can do active beamforming as well as passive beamforming on an end-to-end basis without going through this estimation phase, right? So this should be more like a machine learning-based techniques, right? So you optimize on an end-to-end basis. There have been a few work on using this approach where you bypass estimation completely. And the passive beamforming, for example, can be done based on some code book-based techniques. So you have a predefined kind of, beam forming, right? Predefined beamforming set, you can say, and then you choose one of them, right? So code book-based. Anyway, so for the semi-passive case, as I said, there are some active elements on the RIS, and those guys can transmit, receive signals, and you can use the traditional methods. Now, if you are dealing with a TDD type of system, so basically either the users transmit or the base station transmits. So uplink, downlink channel estimates are like similar, right? If it is a TDD based system. Okay, now this is the case where the RIS has only passive elements, so they cannot, transmit signals, etc. So in this case, people use cascaded channel estimation. So the users, say, for example, send signals and they are reflected from the RIS and received the base station, and then based on the received signal, you can use those least square or NNS estimate. So as I also mentioned, this is the most popular kind of approach, and still this is an active area of research. And people are using also machine learning as well here, right, to reduce the computation, etc., for this cascade channel estimation. But again, our intention here is to estimate the channels separately, and we try to use some machine learning technique. Okay. Okay, this is, I don't want to elaborate probably. This is basically a way of estimating the cascaded channel. So quickly, I mean, if you have got n elements in the surface, you will divide the estimation time into n+1, say, mini time slots, and each mini time slot you send the pilot signal and keep one element on and the other elements off, right? And you collect all the received signal in this matrix here, and then you can use the least squares or MMS estimation. Now it's n+1 because the first mini time slot you keep all the elements off. So basically you transmit the pilot signal, say, from the user side, and it is received at the base station. So you can estimate the direct channel. When all the RIS elements are turned off, then you will be estimating the direct channel. And the other n mini slots you use for basically for n elements, keeping them on one at a time, right? So you get the response from each of the elements. Now, you can say, okay, how do I set the phases, reflection phases of the elements in those mini slots? Now, this is something can be optimized actually, instead of doing random, because if you do randomly, then the SNR may go down, for the received signal. So there are ways to optimize, kind of trying to be more clever, more intelligent in setting up those reflection angles during the training phase to make your training kind of better. You can have a higher SNR, etc. So there are ways of doing it, but I won't go through the details. But this is something also important. You don't just choose the reflection angles randomly, even during the training phase. So you can exercise some intelligence there in setting up the reflection angles. Okay, so this is the code book-based method where you bypass the estimation method. Now, let's go back to our third part of the talk, where basically I'm going to present this machine learning-based method for separate channel estimation. So we consider a MISO system. Okay, so you've got M transmit antennas, and elements in the RIS, and single antenna users. So now the estimation will be done like this: when the users send the pilots, right, and the pilots are received at the base station, right, and then based on these received pilots, we will use some kind of neural network, right? We will use some neural networks to estimate the channels separately. So that's kind of the idea here. Yeah, as we have mentioned several times, the conventional methods estimates the product channel or the cascaded channel, but our case, we're going to estimate this channel separately, G and H. G is the channel between the base station and the RIS, and H is between the RIS and the user, right? Now, this is based on this paper that we wrote very recently. So Firas, one of my graduate students, Amol is one of my former students, Dr. Mazghani is one of my colleagues. So we just submitted this paper in ICC recently. So this work is based on this paper, based on this paper actually. Okay, so the process is like this. We divide the estimation period, like in L time slots, mini slots, whatever you want to call it. So the user transmit a pilot signal in the L time slot, and the base station receives it, right? So phi L is the vector, right? So for the reflection angles for the elements, all elements. So this will be an element vector, right? And NL is the noise. And we collect all these received signals in a matrix. So why is this matrix? And so this can be represented like this. Okay. So this is what we're going to use as the input to our neural network. Why, right? To estimate our channels. Now, the methodology is based on what is called variational inference framework. So if some of you might be familiar with this VI concept. So basically what we want to do is we want to maximize the posterior distribution for H and Z. So say this is the joint distribution. P is the joint distribution of H and Z channel, right? Given Y. So Y is the output, right, that we have observed, the pilot outputs. So given Y, so this is basically the posterior distribution, right? So we want to find H and Z that maximizes this posterior distribution. So if you could express analytically, this distribution, then you try to optimize this posterior distribution to obtain H and Z. Now, in reality, this is difficult to evaluate P, the posterior distribution. Okay. So the idea here is to approximate P by another distribution Q, which should be close to P, right? Because you are approximating, so of course you want this approximation to be close. So you approximate P by another distribution Q, okay? And then your objective is to minimize the approximation error, right? So you want Q to be as close as possible to P. And then you might be able to derive this H and Z that maximizes this posterior distribution. So that's kind of the high-level idea of this variational inference framework. So yeah, so as I said, let's think about the communication system, like in our case, right? You have got input signals, right, as symbols, and which are attenuated by the channel, and you observe the output, right? So now we are trying to estimate the channel. So you can think of like this. Given this output X, we are trying to, observe Z, right? I mean, which embeds your channel here. So if we could find this distribution P, right? This would be like the posterior distribution. And we could try to maximize the distribution to estimate our hidden, the latent variables, which are the channel estimates here. They are hidden here inside this Z here. Now, this posterior is basically given by this. It's like a, if you are familiar with this simple Bayesian statistics, so this is basically how this posterior can be expressed by. So the prior, so remember Z represents those latent variables, right? In our case, the channel estimates is basically the prior multiplied by this likelihood, right? And then here in the denominator, the marginal likelihood. So what I can tell you at this point, the difficulty in estimating, or I mean, in expressing this posterior distribution lies in calculation of this marginal likelihood. So the denominator is actually hard to compute. Prior, I mean, you can assume some prior. Say, okay, the channel is really distributed. You can use some prior, right? The likelihood can be also computed. Given some prior, you can compute the likelihood. But the denominator is what difficult to compute. That's why we want to approximate P with some other distribution so that it's close to P. Because we are unable to express this posterior, unable to compute the posterior, we want to find an alternative, an approximation to this posterior, which is computable. That's the whole idea of this VI framework. Okay, so yeah, so this VI framework enables us to approximate this posterior distribution with a tractable distribution. And subsequently, we should be able to derive the distributions of the latent variables, which are embedded here inside this Z. Okay. Okay, so now let's go to the main, problem here, like the derivation of this Q, right? That's what we want to do. So we approximate, again, we approximate the posterior distribution with a parameterized function Q, right? And we want Q to be close to P. So the main issue in variational inference is finding the distribution, which is close. Now, how do you compare two distributions? I'm sure you are familiar with this Kullback-Leibler divergence, scale divergence, right? Two distributions can be compared by using this metric called scale divergence, right? So if you minimize the scale divergence between these two distributions, then basically they are close. Okay, so this is the measure to see the similarity, right, to closeness of two distributions. Now, without going into the very details, so what we can do like this, the log likelihood of the output signal. These are the output Y, right? The output pilot signal at the base station. So the log likelihood of the output signal can be expressed like this, okay? Where one part is basically the KL divergence between the approximate posterior Q and the true posterior P, right? And this term here. Now you see this log likelihood is a constant. So if you want to minimize this scale divergence, we would like to maximize, we would maximize it. So basically, minimizing the KL divergence is equivalent to maximizing this first term, right? That's it. So basically, our objective will be to maximize this term. And this is called evidence lower bound. There's a name for this. This is called evidence lower bound. So let's go to the next slide. So now, also just for your information, if you have taken a course on information theory, you probably know that KL divergence is always positive, Okay, so that means this log likelihood is lower bounded by this. That's why this is called evidence lower bound function. Okay, so this the first term in the previous slide, right? So this is the evidence lower bound function. And as we mentioned, if we can maximize this, basically we minimize the KL divergence. Okay, so our intention will be to maximize this, and subsequently we will be able to derive the marginal distributions for H and G. So we will get the joint distribution, right? Say we minimize the KL divergence and then we obtain a good Q, right? Which is a joint distribution. Look at here. Now, after you have the joint distribution, we can have the marginal distributions. We can assume some kind of independence between this H and Z, and then we can obtain the marginal distributions. We are done. So that's basically the process. So now if you express this term in negative L, now, so basically we want to maximize this evidence lower bound. Now, since you put a negative here, so it means we want to minimize this L, right? So it's just changing this numerator and the denominator, right? So L will be like a log, Q goes to the numerator, P goes to the denominator. So it's just the convention, they use minus L. So our objective is to minimize L, right? So minimize log Q over P, right? Now, so we'll use some prior distribution for H and Z, okay? And we will be able to express this ELBO in terms of those priors. And basically what we'll do, we'll use a neural network to minimize that ELBO function. So that's the whole idea. So here we use some kind of unsupervised learning. Given some prior distributions for H and Z, okay, which are parameterized by this lambda here, right? So we want to minimize this ELBO, right? I mean, minimize this L function here. And that will end up with a good value of P, good value of Q, the distribution. Okay, so we will minimize this Q by using an unsupervised neural network. Okay, and by doing that, we can have the parameters of the channel, which are given by lambda here. Okay, so assuming that Q belongs to a family of tractable distributions defined by a set of parameters lambda. So remember, we are saying that, okay, we're going to approximate P by Q, right? So Q is something tractable, while P was, we are unable to basically express it analytically. So we use some tractable distributions. Of course, those distributions have parameters, and those are denoted by lambda here, right? That parameters for the tractable distribution. And along with some priors for H and Z, we should be able to derive these parameters, which minimize this L function. That's basically the story here. Okay, so after you hit the joint distribution, as actually I also mentioned, so we basically use what's called mean field approximation. So you assume independence between these two channels, so you can express like this, and you can derive the marginal distributions. From the joint distribution, you obtain the marginal distribution, right? So you get the channel distributions, and then basically your estimates use a sample, right? So you have the distribution, you just take the samples from the distribution. So those give you those matrices. Okay, now the crux of the problem is expressing this L, right, in terms of your parameters lambda. So now for different priors, right, you might be able to express this function, right, LQ in a kind of a closed form. So that's what is given in the paper, but I'm not deriving all this. But what I can tell you, this can be expressed as a sum of these three terms, okay, by exploiting this independence. This LQ term that you saw here, this guy here, can be decomposed into this sum of these three terms, okay? And for different priors, remember, P is like the prior, you can express LQ in a closed form, okay? So as long as you can express LQ in a closed form, that is used as the loss function of the neural network. So in the neural network, you put Y, right, as the input, the pilot signal outputs, and you evaluate this loss function, right? And you minimize it. LQ is the loss function that you minimize in the neural network. So you backpropagate to update your neural network parameters to minimize this LQ, and you stop when basically you minimize it, right? Or you finish your predefined number of iterations, whatever. So you minimize this LQ, and by doing that, you obtain the lambda, those parameters. Okay, so this is how it's done here. So you've got two neural networks, one for G channel and one for the H channel. Okay, so basically the received signals that you got, you fed, feed them here, and you will, after it's trained, right, you get the values right away. But for training, you will minimize this loss function. Okay, so given the received signals, the input, the neural network will predict the parameters, right? So they will output the parameters such that your ELBO function, right, is minimized, which means your KL divergence is minimized, right? So they are good parameters. So as I said, after you have the channel parameters, say if you are assuming some Gaussian distribution, if your posterior distribution is Gaussian, so you got the mean and variance out of this neural network, and then you just generate your samples. right? So that's how you will fill out those matrices. Okay, so now for Gaussian prior, so if you assume kind of a relay fading channel, so you will you can assume some Gaussian priors and the expressions for P and G. So these things will be required to evaluate your ELBO function. Remember, so these expressions are required for the evaluation of the ELBO function. And posterior distribution here is also assumed to be complex Gaussian with different mean and variance. So basically what you will do, the neural network will estimate these guys, the mean and variance of the posterior distribution. Okay, so so now these will be required again in the evaluation of the LQ. And you are able to express the ELBO function in a closed form in terms of all these expressions. Okay, now what do we also do? We basically evaluate for two cases where your priors are Gaussian, also for the case where the priors are complex Laplacian. Now, these kind of priors, like Laplacian channels, if you want to say, they are more realistic for millimeter wave propagation. So a relay fading channel is not really, may not be appropriate with a large RIS because of the sparsity of the channel. For sparse channels, relay fading is not a good model. So you may use this kind of Laplacian channel. So again, we will express these, we will derive similar expression for the priors, like for the P, for the G channel and the H channel, and also the posterior, right? We'll express this. And for Laplacian channels with mean zero with some, they call it scaling parameter. So we are able to, again, evaluate this ELBO function in terms of this Laplacian priors, okay? And we can use it in the neural network, right? As a loss function, okay? Okay, so that's basically the approach, the variational inference-based approach for channel estimation. And again, we are estimating the channels separately, right? So we are finding the distributions of the channels by maximizing the posterior. Because the posterior, we can express it in a nice form. We approximate it by a function Q such that the KL divergence between P and Q is minimized. So that's basically the moral of the story here. Now, I will quickly show you some of the simulation results. Oh, I think I'm running out of time, I guess. Give me just 2-3 minutes. So,
sure, no worry. Yeah.
Yeah, so now we evaluate the method in terms of two metrics, actually, the capacity, from the transmitter to the receiver, the capacity. The capacity that we can achieve with these estimated channels and the one that you achieve with perfect channel, right? So then you can compare how good is the estimate, And also in terms of the normalized mean square error. So these, if your H and Z are the true channel, right? And H hat and Z hat are the estimated channels. So you can compute the normalized mean square error. So for the vector, H is a vector because it's a single antenna user. So here is basically the norm. If you take the difference, right, of the vectors and then norm square. And here is, because G is a matrix, right? So it's like a Frobenius norm of the difference. And then you divide by the Frobenius norm square. So this is F, basically the Frobenius norm. Okay, so for the neural network, we have, these are the parameters here, 2 hidden layers, 300 neurons, and activation function, etc., and the learning rate 0.001, etc. Okay, so 64 elements in the RIS, 4 transmit antennas, and I don't see here 50 pilot symbols. Yeah. Okay, so this is basically the capacity, the top one, the black one, with the ideal channel estimates. and this blue one with the proposed estimate. So as you can see, with high SNR, basically it works very well. The estimates seem to be very good with high SNR. So you optimize the reflection angles, right, based on the estimates. And here you optimize the reflection angles based on your true estimates, assuming that you have the true estimates available. And the red one is for the random case. So basically, just to show that, you know, if you do random phase shift, right, without doing an estimation, just do randomly, right? So what you can get. So, so the point is, at high SNR, the estimate seems to be very well, you know, and gives capacity same as the ideal capacity. Okay. Now this is the NMSC. Now for the relay fading case, where we use the prior to be like complex Gaussian, as the SNR increases, the mean square error decreases, especially for the H channel. For the Z channel, it does not change much. This is basically due to the way we calculate, because when you calculate the Frobenius norm-based estimate, I mean, this can happen, you know. I mean, due to the nature of, you know, the way we calculate the norm, I mean, in this case, so this is doesn't really change much. Okay, so this is, I guess, the reason why. In this case, for Gaussian priors, the Frobenius norm, I mean, does not really give you a very good, you know, what do I say, like the approximation, right? It's hard to see how good is the approximation, because it doesn't change much. But we'll see for the sparse channel, like for the sparse case, because there are few elements, right? So the difference becomes more observable. I think that's how I should say it. So when you have got fewer elements in the matrix, because in sparse case, many of the elements are basically very small, 0, right? So in this case, the difference in the norm, and then you take the square, then you see quite a significant difference, right? So as SNR increases, you see a reduction in the mean square error. And also you see reduction for the H here for both the channels. And similar to the previous case for the sparse channel, also, in fact, it's much better here. Even in lower SNR, you get a closer capacity here. Of course, at high SNR is very close. So looks like the method is better even, you know, for the sparse channels, like a mmWave kind of channels. Okay. Okay, I think that's also to summarize in this talk. Basically, I have discussed a joint channel estimation framework as well as separate channel, because from the joint distribution we basically obtain the separate channel distributions for the transmitted to RIS and the RIS to user channel. And we have also considered the sparsity of the mmWave channels. And what we have seen, sampling from these estimated channels, right, gives us capacity which is close to the true capacity, right, with the perfect estimates. Now, as far as future extension of the work is considered, we should probably consider more physically consistent RIS modeling, because the RIS modeling is kind of a abstract here, but there are phenomena such as multiple reflections, etc., inside the RIS, which can be also considered to have a better kind of a physically consistent model, which can be incorporated in the channel modeling. And also robustness of the method can be checked for different channel priors. We did it only for 2 cases, but maybe we should do it for other channel models as well. Thank you. I'm sorry, you know, I got a little bit.
No worries, no worries.
Yeah,
Thanks, Professor Ekram Hossain, for your nice, insightful talk. So probably we can take 2 or 3 questions, I think, because of the timing.
Sure.
That's
sure.
one from the
Please go ahead.
Q&A box.
Yeah, sure.
So he or she was asking, we need to do passive beamforming at the RIS, and for which cascaded channel is enough. So he or she was asking, why do we need to do the channel separately? And basically, he or she was asking what the purpose of doing, or the motivation of doing the channel separately instead of just estimating the cascaded channel.
Yeah, no, I think it's a good question. In fact, I already answered this before, because I said for many cases, like as you have mentioned, for passive beamforming, the cascade channel might be enough. You don't need to separate, estimate the channel separately. But in some cases, it may be required to have the channel separately. Say, for example, if it is a modulating surface, if you're doing like a scattering, I mean, if you want to modulate the reflected waves, you want to, embed some information, like they are called modulating surfaces. So in those cases, you may need the channel between the RIS and the user maybe separately. You know what I'm saying? So for certain applications, such as, again, I'm repeating, so modulating surfaces, you may need to have the channel, say, for example, RIS to the user. And also another thing is, I mentioned as well, like the channel between the base station and the RIS is rather static, I mean, you may estimate that channel off and on. You may not need to do it very frequently. On the other hand, the RIS and user channel may require estimation more frequently, so instead of doing this cascade channel estimation every time, maybe you can adopt some other approach where you do a different time scale, maybe, because the one channel is rather static, other one is more dynamic. So there could be cases where you may benefit from separate estimation. So that's what I probably can tell.
Thanks. But one additional question related to this one, like because as you mentioned in the slides, right, there are some ambiguity issue if we want to do the channel estimation separately. So so I would like to ask, in your approach, like variational inference, so when you evaluate the performance at the end, I say you show some results like normalized mean square error for G and H. So in that case, do you consider this ambiguity, or you already eliminated all the ambiguity when you do the performance evaluation?
So you mean ambiguity? Sorry, I probably missed it. So ambiguity due to what?
Because as you mentioned in one of your slides, right? If you multiply.
Oh, yeah. Okay. I see. Yeah. Yeah, no. So here basically no ambiguity here. So I mean, it's here that D thing, right? That D matrix, right?
Yeah.
No. So we are not estimating. We are not using any like a separation, like what we call like a factorization, right? It's not like, okay, we are factorizing the cascade channel into two channels, right? It's like a matrix factorization problem, right? If you look from original, but here we are not factorizing. So that question does not arise here. Okay. So we are not really going that way. We are bypassing, that ambiguity somehow.
Okay, Professor Eric, as you know, there are many existing approach in the literature. Model-based, data-based. Even for me, I have done some work on the channel estimation for this passive RIS-Aided MIMO system. So like people use the conventional compressive sensing.
Yeah, compressive sensing. Yeah, of course.
So could you please briefly summarize, what would be the advantage and the disadvantage of the model-based scheme and your new scheme, like AI-based schemes?
Very good question. Well, I can tell you guys know better than me, okay? I have not done really many work on this. Now, I also mentioned this. This is more a runtime efficiency, right? if you do these compressive sensing based methods, I think computationally they are not simple. Am I right?
Yes, but for the AI-based
for the
scheme,
large,
the training.
No, yeah, training. Well, I mean, so
Yeah.
For large matrices, for large systems, right? I think you want to have more runtime efficiency, right? Now,
yes,
this is just the first step, I should say, because we want to have low overhead, right? Low complexity estimation. And obviously, what you want to do, you don't want to estimate every coherence time. Using some prediction will be really good, right? To avoid this overhead. Sure. Okay, so what could be done is you mix these two, hybrid, right? So you send pilots off and on, and then occasionally use prediction. Now, if you could use this variational inference, say, for example, to predict the covariance matrix, channel covariance matrix, and for a rather quasi-static channel, you can avoid this pilot transmission every, you know what I'm saying? Yeah. So, in fact, at this point, we are trying to estimate the covariance matrix. Okay, instead of just the distribution, the covariance matrix, so that we can basically predict a little bit, you know, instead of just doing it, you know, inference every time. Maybe we can predict. So that's how you can also make it computationally a little bit better, because you can argue that, well, every time neural network also has some computation involved, right? Even for inference. Even from inference, you have some computation. Of course, training is an overhead, if you say. And then inference also has some computation involved. But if you do prediction, maybe you can even make it better, you know, less computation, you know, improve. So now this is one approach, but you can use, end-to-end approach. As I said, like completely bypass this estimation. You just do end-to-end, right? You do, you know what I'm saying? You do your optimization end-to-end basis. So that's another approach. Now, you are asking me about all sorts of different approaches, right? So now, even in pilot-based transmissions, there are scopes for optimizing, like number of pilots and, you know, pilot design, you know, etc. Even the waveforms of the pilots, because if you want to minimize this pilot contamination, all these kind of things, you know. So there are also some different, I think, choices possible, even within the pilot-based schemes. Again, I'm kind of repeating, I guess. And you can do hybrid pilot and prediction. Maybe you can do more on the prediction side, right? Now, the neural networks, of course, can be used. ML techniques could be used in the prediction, probably, you know. You use LSTM type of thing, you know, for a time series, and maybe you can do good prediction. So machine learning will have potential, you know, benefit in prediction, right? In addition to using in a direct method like a pilot-based, where you want your objective is to improve runtime efficiency. That's one thing. But for prediction, you can also use this machine learning, right?
Yes.
So in contrast to the conventional methods where you resort to computation, this compressive sensing and other, I mean, they are more a computation intensive. So
but for the machine learning techniques, I'm not sure about this extendability, like from one scenario to another scenario.
Well, I mean, now, no, there are solutions. You can use this meta learning and all this kind of things.
Okay,
so
transfer learning.
Do it. Transfer meta learning is even the incremental learning. They call it continual learning, right? So there are, you know, I mean, there are some choices that are worth trying, probably, you know, to improve the generalization.
And maybe one last question from me, because I think the audience they only have one question. So, and one last question from me, like that. I mean, for the you also mentioned about in addition to the channel estimation scheme, you also mentioned about the code book based one. I mean, if we utilize a code book, then we can skip channel estimation at the end. But as you know, I mean, usually for the RIS or partial RIS, they have the hardware constraint. It's like a constant modulus for each element, and also they have a large number of elements. So do you have any guideline for us to design a very good code book and that can be used for such a scenario, like a RIS-Aided system?
Yeah, well, as I said, I'm not probably an expert, but I can tell you a little bit probably. Now, if you've got, as you said, you've got large number of elements, right? Maybe hundreds of elements. So of course, what you can do multi-beam training, right? It's like I think what I understand, you can divide the elements into some groups, right? And one beam for each group to scale it at least linearly, you know? You know what I'm saying?
Yes.
So basically doing some grouping and design, you know, beam patterns for groups maybe, instead of doing for every element, right?
Yeah.
So now in reality, actually, that's how the meta surfaces work, because when you activate the elements, you don't just do activate each element at a time. You basically do it row column, you know? In reality, they call it what channel, they call it channel in the electromagnetics, those guys. So now going into further detail, I mean, as I said, from computation point of view, doing some grouping may reduce the complexity, right?
Yes.
And I think there are a few work probably also in this direction where they use this grouping concept, and I think they call this multi-beam training.
Okay.
Yeah. So, yeah, I mean, that's probably one obvious kind of way to reduce complexity, and maybe using some hybrid approach, right? I mean, you embed. I think in reality, what can happen, they may not be fully passive, you know, you may need to have some kind of processing in the RIS as well. I mean, semi-passive type of thing, and then probably that will facilitate this thing. Otherwise, everything has to be dictated by the controller, right? So
yeah, because nowadays there are many variations
actually,
for RIS, like hybrid RIS, and
exactly. So I think to be more practical, I mean, you may not have fully passive, you know. I mean, you may have some active elements, some active processing also need to be incorporated. I mean, you know, and depending on the application, one solution will not fit for sure every scenario, right? So
agree,
I think in reality, for practical deployment, I think you may need to go for different choices actually. So, you know, compromise, right? So you need to make a trade-off. Yeah.
Okay, that's all from my side. Thanks a lot, Professor Ekram Hossain, for giving us a very insightful talk. I think this is also a very timely topic. I mean, many people working on RIS for channel estimation for other purposes as well, like an optimization. So it's
thank you very much for inviting me. Yeah,
and also thanks for the audience for attending this seminar. And I guess that's all for today. And have a nice day, Professor Ekram Hossain.
Thank you very much. Yeah, so if you folks have any questions, let me know.
Face-to-face discussion next time when you are here.
Sure. Yeah, hopefully next year. If you guys have 6G Summit again, maybe next time.
Yeah, sure, of course. Yeah. Have
Okay,
a nice day. Yeah, take care. Bye-bye.
Thank you very much.